Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. Most students get comfortable once they master the basic formulas for circles and squares. But in the real world, the relationship between variables isn't always handed to you on a silver platter. Sometimes the link is hidden in the geometry of a shadow or the ratio of a water tank. Today, we're leveling up. We're moving beyond the simple formulas to discover the hidden constraints that make intermediate related rates problem both challenging and rewarding. Now, before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. For our first example, we have a 6 feet tall man who's walking away from a 15 feet lamppost at 5 feet per second. We're going to start by drawing a diagram to represent the situation. So here we have our lamp post. So I'm just going to draw a light bulb here to show that this is a lamp post. And we know that this is 15 feet. Next, we have a man who is walking away from it, and his height is 6 feet. So he is walking in this direction, which is away from the lamp post. Now we can see if he's on this side of the lamp post, then this is going to cast a shadow that has a length of x. So this is our shadow. Now, just to demonstrate what this would look like, if, let's say, this guy walks all the way to here, then we can see that his shadow is going to be changing in length, because now the length of his shadow is going to be a little bit longer. So now recall that the step one of solving a related rates problem is to set up an equation. So how do we set up an equation here? So I am going to draw a horizontal line from the base of the lamp post to the end of the shadow. And notice that this here is a right angle triangle. So since we have named the length of his shadow x, I'm going to label the distance between the base of the lamppost and the man G for ground. And notice that we also have a right angle triangle formed by this man here and the shadow that he's casting. So here we actually have two similar triangles. The first one formed by the lamppost, this entire base, and then this hypotenuse here. And then the second triangle is formed by this man, his shadow, and this hypotenuse, since they're both right angle triangles and they share this angle right over here. So this means we can go ahead and set up a ratio between those two triangles. So step one, the equation that we're going to set up is going to be the height of the large triangle, which is 15, over the base of the large triangle, which is G plus X. And this is going to be equal to the height of the small triangle, which is the height of the man, that's 6, over the base of that small triangle, which is just a shadow, so that'll be x. And we're just going to go ahead and simplify this a little bit before we move on to step 2. So we get 15x is equal to 6g plus 6x, which means 9x is equal to 6g. And we might as well isolate x because that's eventually what we want to find. So we get x is equal to 2 over 3g. Now step 2, we're going to differentiate both sides with respect to our independent variable. So again, our independent variable here is time, because looking at the units here, we have feet per second. So we're changing with respect to time. So taking d by dt of both sides of this equation, we end up with dx dt is equal to 2 over 3 times dg dt. And now the last step is for us to substitute in the values that we know. So here we're told that this man is walking away from the lamppost at 5 feet per second. So looking at the diagram, what that means is g is changing at 5 feet per second. Or more accurately, it's increasing at 5 feet per second as this man walks away. So that means this 5 feet per second here is dg dt. So we can go ahead and substitute that in, which means we end up with dx dt is equal to 2 over 3 times 5, which means dx dt is 10 over 3 feet per second. And that would be our final answer because x here is the length of his shadow. So dx dt equaling to 10 over 3 means the length of his shadow is increasing at 10 over 3 feet per second. For our next problem, we're looking at pouring water into a tank, and we want to figure out how quickly is the water level rising when the water is at a certain depth. So again, we're going to start by drawing a diagram. Our tank here is in the shape of a cone, so it doesn't specify which side is up. So we're going to say that for this problem, the pointy side is down. And we're going to draw a sideways cross-sectional view of the tank, which means it's going to be in the shape of a triangle. So let's say that the water level is right over here. Then that means this is going to be the height or the depth of the water. But we're also told that this entire tank has a height of 10 meters. So that means from the top of the tank to the bottom, this is going to be equal to 10. And the radius is 4 meters, which means from the side to the center, this is going to be equal to 4. So again, notice how we have a similar triangle situation here. So here, this would be a right angle triangle, and then same thing, formed by the surface of the water, we have a right angle triangle. So at the water surface, this is going to have a radius of r, so we're going to call this here r. And now we can go ahead and set up our equation. So step 1, using similar triangles, we get that r over h is equal to 4 over 10. Which means r is equal to 2 over 5 times h. Next, we know that the water is being poured into this tank at a rate of 2 meters cubed per minute. So this 2 meters cubed per minute is telling us that the volume is increasing at that rate. Which means in order for us to use that number, we need to go ahead and write down the volume formula for a cone. So the volume formula for a cone is V is equal to 1 over 3 times pi times r squared times h. And now, because we know r is equal to 2 over 5 times h, we can go ahead and substitute that in, which means we end up with V is equal to 1 over 3 times pi times 2 over 5h squared times h. And then simplifying that, we get this is equal to 4 over 75 pi times h cubed. And now we have the equation that we need so that we can start differentiating with respect to t on both sides. Now, some of you might have noticed that we did a substitution for r instead of h, but we could have also done it the other way around. But the reason we did it this way is because we need to look at what the question is asking. The question is asking how fast is the water level rising when the water is 5 meters deep, which means the final answer that we're looking for here is dH dt, because we're looking for the change in height of our water. So if we had done it the other way, where we substituted in an expression for h, then we would have lost our h, and our equation here would only be in terms of r, which would not be useful for this particular question. So it's always a good idea to look ahead and see what you're trying to solve for when you do substitutions like this. So now for our step 2, we are going to differentiate both sides of the equation with respect to t, which means we get dv dt is equal to 4 over 75 pi times 3h squared times dh dt. And now our step 3 is going to be for us to substitute in the values that we know. We're told that water is being poured into this tank at 2 meters cubed per minute. So that means dV dt is equal to 2, because that's how quickly the volume is increasing. And then the other value that we know is that at this particular moment in time, when we're trying to figure out how quickly the water level is rising, the water is 5 meters deep. So that means h is equal to 5. So substituting both of these values in, we get 2 is equal to 4 over 75 pi times 3 times 5 squared, which is 25, times dh dt. So now 3 times 25 is 75, so that gets canceled. And then isolating dh dt, we get dh dt is equal to 1 over 2 pi. And our unit here would be meters per minute. And now let's do a quick recap of what we covered in this video. We saw how in both of these problems, we had too many variables to start, but we used similar triangles to create a relationship between them before we started differentiating. And you can use other tricks like trigonometric identities to do that as well. And then in our second example, we saw the power of pre-substitution, which was used to simplify our equation into a single variable, because it's much easier to differentiate volume as a function of height than it is to deal with a product rule that involves both the radius and the height, especially since the problem didn't even give us any information about the rate of change for the radius. So you want to take a look at what the question is asking for in order to decide on the direction of the substitution. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.